Hello and welcome to another open source silicon stream. And we're up to number 6 now. So if this is your first time tuning in, then welcome. It's going to be a regular thing, although I did miss last week because I was traveling to Copenhagen. More on that later. So usually 5 o'clock Central European time on Mondays. And you can watch the old streams. They're all like on the YouTube channel. So say hi in the chat. Tell me what country you're currently watching from. Feel free to ask questions at any time. That's kind of one of the ideas of this experiment. And if you want to get more involved, then there's a few options for you. You can join my mailing list on 0to8course.com. You can join the Tiny Tapeout Discord at tinytapeout.com/Discord. You can make a tape out on Tiny Tapeout 10, which is closing imminently in about 10 or 15 days. And you can also sign up to one of my more in-depth courses. I've got a digital course and an analog course. So hi, Rohan. Welcome to the stream, watching from India. And going to kick off just with some news. So let me add my screen here. So yeah, I mentioned I missed last week because I was in Copenhagen and had a really great experience running a workshop with Martin, wearing my ASIC chain as usual. Good turnout, about 80 people. There was a professional photographer there, which was nice. Get some really nice photos. That was everybody together. So thanks to the Danish Chips Competence Centre, Edu4Chip, Synopsys and ScioSil for sponsoring that event. It was really good fun. And we got most people to do a tape out. Oh yeah, and I saw Thomas there. Hi, Thomas. Thomas says hi. Thomas Flummer was there. A couple of other people I knew from kind of Hackaday and tech conferences, and we had went out for a nice dinner afterwards. Demo scene entries. So if you've not seen the Tiny Tapeout 8 demo scene entries, they've been all joined together and put into this one video now. And there's a little thumbnail, and you can click on here to get access to the design and to watch it. It's really worth checking those out. And Tiny Tapeout 10 closes in 14 days, and the Tiny Tapeout 10 demo scene competition is open, and it's free to enter. So if you enter design, you even get a free tile for entering. So it doesn't cost any money to get your design on the hardware. Got some new chip scans from Tiny Tapeout 7. So I'm going to be posting a bit more about this later, but this is top metal, and then this is the substrate of Tiny Tapeout 7. And then we've got some quite nice, I think these are electron microscope images, getting a little bit closer in on the details here. So they'll be posted up soon, so keep your eyes out for them. Okay. eFabless Chip Chat number 5 is happening shortly. When is that? February 25th. So that's tomorrow at 9 a.m. Pacific time. So that's will be 6 o'clock Central European and 10:30 Indian Standard Time, I think. Worth checking. So if you want to join that, that's always good. Getting access to the eFabless experts and being able to ask your questions. And you can also check out the previous ones on YouTube. And then there's FOSSI Latch Up. So registration and call for speakers is open now. The plan is May 2nd till 4th in Santa Barbara in the US. So if you're on the West Coast and you want to join another cool FOSSI event, then check out Latch Up 2025. We just had Yosis Users Group 10, which is especially relevant to us. ML did a presentation on ASIC synthesis with Yosis, covering Yosis and ABC and some new features for ASIC, and that's just been published here, so feel free to check those out. And then just a couple of things, Tiny Tapeout related. Remember to post using the hashtag TinyTapeout or tag us in your favorite social network. So Anton did his first mixed signal design, and one of the things I really liked about it was his this interposer board. So it's an analog and digital project, and you can kind of plug this interposer in, and that gets you the VGA output. And that's the design. Some simulation results. And there's so it needed a little op amp there. Final interposer board. And this is a little bit older, but just in case you didn't see it, Carsten Wolf, who did a really interesting SAR A to D on Tiny Tapeout 6, he brought his chip up, made some measurements, and posted a video about it. Ran into a couple of issues, but has since worked some of those things out, and he posted a reply here on LinkedIn with his updated measurements. So worth checking that out if you want to find out more about an interesting SAR A to D from Carsten Wolf, who's principal IC scientist at Nordic Semi. Okay, so I think that's all the news. And today for the topics, what I want to look at is doing a MUX experiment and level shifter. So I think it was on, I should label these. Yeah, it was this one, I think. Number 4. Looking at what happens as you reduce the voltage of a digital block supply. And I started doing a layout there of a digital design. And I want to continue a bit on that today. So this was the original idea. So the Tiny Tapeout device under test goes in here, and I drew all this extra stuff just to kind of remind us that a design inside Tiny Tapeout isn't on its own. There's other aspects you have to care about, like the muxes before and after. And we have these analog muxes as well with transmission gates. And my original idea was power the device under test with 3.3 volts. And then I can just turn down that 3.3 volts and see what happens. But Sylvain pointed out that the transmission gates are powered by 3.3 volts as well. So lowering the voltage there would also affect those output analog signals. Then the second idea was use a level shifter. And that also has a problem, which we'll get into. And then this is the kind of third idea now, which needs a buffer and a level shifter. And we're going to have a look at that today. But one thing that we didn't do from the previous stream was actually do an experiment. So I think the first thing I'm going to do is just see what happens. Going to remove a 0-ohm resistor from the board, get this factory test running, select the design, and then just lower the voltage. And I've also got Sylvain's joining here as well. Hey Sylvain, how's it going?
Hi, can you hear me?
Yeah, I hear you, yeah.
Okay,
yeah.
Good.
Yeah, so I invited you to join because you came up with this great idea for this, the level shifter, because I came up with a kind of crappy one that we can look at later that only worked down to a 1 volt, and yours works down to 0.2 volts. But the thing
with simulation at least.
Yeah. Well, I guess we'll see next year. what I want to do first is, I think I've got this board over here. And this was actually, I think it might have been the one that you sent me. Do you recognize it? It's got like
Yeah,
little.
probably because it's got the little wires rather than the real resistors. So that's probably
That's it, yeah.
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 Yeah, for sure.
So I'm going to cut the 1.8 volt one and then supply 1.8 volts from the power supply, enable it, select the factory design, start it counting, and then just slowly turn down the voltage, the power supply, and see what happens.
Yeah.
What's your prediction?
I think it will work down to maybe 1.1, something like that. It will be slow. Like you will, if you try to send, like if you select like the factory design, something like that, it will definitely slow down. Because the thing is, the default standard library we use is the HD one, and the HD standard library uses the standard VT NMOS and the high VT PMOS, and so I think they have like a VT of something like 0.8 volt or something, and that's really when they just start to turn on. And so for them to actually drive with any strength or anything like that, you need like 0.9 or 1 volt. And at that point, they're still really slow, as in like hundreds of nanoseconds possibly to change a node. So yeah, at about 1.1, they will start doing something that you can count on, I think. That'd be my prediction. I don't think the flip-flops or like the muck selection or anything like that will have any problem because it's stable. It should be stable. It should keep its state even at low voltage. Yeah, that's what I think. And I think that's also why when you did your voltage level converter, it stopped working at around 0.9 volt. Is that that classic level converter topology really only works when you can actually count on the MOSFET turning on, which is not the case when you go to 0.8 or 0.7 volts in Sky 130 at least. I'm actually trying now to run a quick simulation of the transmission gates to see how they would work at 1 volt. Because I'm curious. I assume they're not going to work very well at all, but I didn't actually simulate it, and I thought, okay, I can do that. So you're just putting a jumper at the moment, right? I guess you don't have a mic on you, because we can definitely not hear you. So, Tetzelbrum, you are aware of the Chipaloza level shifter. I looked at some of the level shifter that are on Chipalooza, but on some of them they actually use the HVL library. I saw some other designed by Tim that he used on some other things, but they're also they're really meant to convert from like 1.8 to 3.3, like from the core voltage to the IO voltage, and they're not really meant to work on very low voltage. If you have a link, okay, you can't actually post link in the chat because that doesn't work. But if you have some reference, you can point me to some specific one that would be made for low voltage. But as far as I know, the one in Chipalooza are really from core voltage to IO voltage and not anything special. In the simulation, which simulation do you mean from the FF to SS corner? Yeah, I haven't done it yet at the moment. I'm just running it on TT, and it's honestly the first results I got are really not looking good on TT. Like the analog transmission gate running at 1 volt, you can get up to, yeah, it goes up to like 1 kilo ohm of resistance. Of RD, the measured RDS on goes from up to 8 kilo ohms, and that's the TT corner. So on SS, it's gonna be even worse. So yeah, as I predicted, the analog gates are not usable if you lower the VA power down to such low levels. Yeah, I can imagine. I did he hasn't shown it yet, but the level shifter that Matt talked about, I did simulate it in all 5 corners. So SS, TT, FF, and then FS and SF. It works on all of them. And honestly, we don't need it to work that well because it was tested at down to like 0.2, 0.3 volts. But the reality is that the rest of the logic will start breaking down way before the level shifter. So that's all we need from the level shifter, is that's the thing that breaks last. And I'm pretty sure the HD standard library from the foundry will break down at those voltages way before the level shifter does. So that's really all we needed to do. Matt, in case you can hear me, we still can't hear you. I'm not sure if you.
It's because I need to be added to the stage again.
Okay.
Yeah.
Now we can hear you.
Yeah. Yeah, just as well. I haven't been talking this whole time. Yeah, so I've kind of removed that jumper, and now I'm supplying 1.8 volts. Am I actually supplying it there? There we go. Forgot to turn on the power supply. Now maybe this is gonna work. That's weird. Okay, but it's detected the shuttle now, and I can enable this. And if we set that to 1, should see. Can I make this bigger? Okay, but you can't really see that. But I think I also need to turn on.
Yeah, one of the UI, I think.
Yeah, so I think that's counting now.
Yeah, we can see slightly the. Yeah, we can see it well now.
Okay, and you can see on the PSU that it's 1.78 volts at the moment.
Yeah.
Maybe I'm going to put the scope on as well.
You'd need like one of those cable to directly connect the 8 output of the PMOD to the 8 digital channel, so that with one cable you can connect
Yeah, that'd be cool. I should make one of those. I think there's something that's similar, like the logic analyzer, but I want to see the analog signals, don't I?
Hmm.
Let's change this to 100 hertz. All right. Let's see what happens when I turn down the voltage. All right.
How much is that? There's a cable in front of the display, so I can't read the first digit. 078. Okay.
0.78. So at 0.8 looks like it's fine, and then at 0.8 it looks like it's doing something pretty weird.
Yeah, not everything is toggling normally, I think.
So I'm not totally sure what I'm looking at here. This is outputs 0 and 1.
That's weird. As far as I know, they should be like just divided clocks. So yeah, that looks more like what I would expect. Yeah, that looks more like what I would expect.
Okay, so I'll turn down the voltage again. Well, you don't really see it stopping on the scope though.
Yeah, no, you do.
Yeah. There you go. Okay. Just on the edge of working there. 0.78 volts.
Yeah, it's much lower than I would have expected, honestly. But
Okay.
you're pretty slow, like at 100 hertz. Like if you
Yeah.
try to feed like 1 megahertz,
Okay, yeah, you can even see the
yeah, the PMOS have a hard time bringing the signal up, so
there's the metastability happening right there.
uh,
So it looks like it works good down to 0.8. These are kind of more nominal. And then there we run out of time. That's cool.
no, it's not a ring oscillator. The RP2040 is providing a fixed frequency, in this case 1 megahertz, and it's being divided down. So it's the counter, basically.
Okay. Hello, Society of High Sciences. Greetings. All right. So, yes. So coming back to here then, this isn't going to work because the transmission gates are also supplied by the 3.3 volt rail. So the second idea from Sylvain was use the mux as normal, because we see the mux is working. But we would need to provide as the voltage gets lower and lower, the high voltage output is not going to be high enough for the PMOS to drive a good high signal. So we need a level shifter. And then we can, on the 3.3 volt, we can actually supply at 1.8 for the core voltage and then control that. But then the signals that the mux will see will be level shifted up to 1.8. That makes sense, Sylvain?
Yeah.
And then this was something that I thought was interesting as well, because I wouldn't have thought of, I don't think I would have thought of this, that we were going to need to use an input buffer. So my understanding here is that when we power up this DUT here inside from our variable voltage supply, and we've put like 0.8 volts in or whatever, then the N wells are going to be biased to that 0.8 volts instead of the normal 1.8 volts. And that's going to cause a problem for some standard cells when they get a high voltage, because it's going to be higher than the N well is biased. Is that right?
Yes. Like a bunch of normal logic standard cell, like a OR and or buffer, stuff like that, the input pin just goes to the gate, and that doesn't pose a problem because the gate is electrically isolated, and since the oxide is thick enough so that it can withstand 1.8 volt, because that's what it normally runs on. So that's not a problem. But some of the standard cell, including, for instance, the flip-flops and most importantly, the MUX 2 and 4 cells, they use transmission gates, which mean that the input of your external signal goes to the source of and the drain of some NMOS, and so at that point you need your NWell to be biased properly, or else you just end up with a diode basically between the drain or source of your PMOS and the NWell, and current will flow from your input to the NWell. So that would be a problem. And so the easiest way to avoid that is just to make sure that you have, as the first cell, is just a normal buffer or an inverter.
Right. Okay. So then this is the final design that I'm working on. The buffer, I can just use like standard cell buffers, like you mentioned, Sylvain, but the level shifter needs a little bit of extra work. So here's what I have at the moment. And this was suggested by Sam Ellicott, I think, in stream number 4.
Yeah, so that's basically the classic level converter, like the most, at least in the literature and stuff, that's always the one I've seen. But
Yeah.
one of the problem with that is that first, the inverter to generate the invert signal actually stops working pretty early itself, and then the rest cannot work.
Yeah.
So yeah.
Yeah. So I tested this. Took me a little while to get it working, but I made this little loop. I always find the control language of ngSpice hard, and I don't know why, but a lot of the references were putting this in curly braces, which wasn't working, and it's got to be like $ampersand for some reason. I don't understand why. But that lets me alter the supply voltage from 1.8 down to 0.5 volts at 0.05 volts increment on both the supply voltage and the input pulse. So should be able to simulate that. Although it looks like it's going a lot slower than it was on my other computer. This is going to take too long, I think.
Do you have ClearView enabled on SpiceNet? Yeah.
Yeah.
Is it the same ngSpice version?
It might be a different ngSpice. No, I think that's the same one I've got on my laptop. Well, maybe we can leave that running anyway. And
how many steps are you making between?
Yeah, actually, maybe I'm just going a too small an increment. I don't know. Where am I at now? 1.4. I'll leave it running. we can have a look at your one. I don't know why it's opened in the same window. That's really annoying. All right. So this is your version.
Yes. And let me just preface that I'm not an expert chip designer, but the idea was just basically to make an analog comparator. And so it's on the right, I mean, on the center side, you basically have like your classic op-amp OTA circuits with the current mirror at the back, the differential input pair, and then the current mirror at the top. I didn't want to use like a big poly resistor, so to set the current, I'm just using M3 as basically a resistor. That's basically what M3 is doing. So you can see it's actually very long MOSFET. It's a very narrow 0.42. It's the minimum width, and it's fairly long 0.6, so it limits the current. I think the current in that branch is in the order of a few microamps. But it's not that critical, because since I just want a digital output, like a 1 or 0, I don't care too much about the exact bias current. So the process variation between FF and SS will vary the bias current significantly by, probably double it or something between the slowest and thing, but it doesn't really matter for this application because I just want a digital output at the end, so that's fine. And it's smaller than a poly resistor. I used PMOS for the differential input pair because your op-amp, you can do it in one direction or symmetrically using NMOS as the input pair. But here I chose PMOS because my inputs are going to be low voltage, and so I want my headroom on that side basically, so that my PMOS, even at very low voltage, like 0.2, 0.5 volt or something like that, they will be not operating in a subthreshold. And finally, I'm just the transistor pair on the far left, but that's just a voltage divider, basically. From VDL, it tries to generate a voltage that's somewhat intermediate between both, and the transistors have been scaled such that it's more or less in the middle. And so the analog comparator compares the input signal to half the rail and then transition its output like that. And then because the output of the first stage is not full swing, there is after another CMOS buffer that will basically restore it to nearly full swing on that end. And the transistor size that are there, like they're just first draft guesses sufficiently so that it works. Some of them could be refined, and then the number of fingers or so altered so that during the layout you can properly match, M5 with M6, M7 with M8, M2 with M1, that kind of stuff. Something else that when I did a bit more simulation would be useful is on SRCN, they actually put a transistor to act as a capacitor, like a MOSFET, so like a NMOS biased with its source and drain connected to ground and the gate connected to SRCN, simply because at very low voltage, those two transistors pass really, really tiny amount of currents, which means the impedance of that node is very, very high, which means that it's easily influenced by the node out P here will vary slightly, and through the parasitic capacitance between the gate and drain, some of that signal can end up on SRCN, and so to kind of prevent that node from moving around too much. Adding some capacitance on SRCN is helps.
I had a question about the sizing on these.
Yes.
I was expecting to see a wider PMOS to match the NMOS.
I mean, it's not really. Yeah. Here, instead of making the PMOS wider, I made the NFET longer. But it's always the W over L ratio that matters, right? So here, technically, the NFET is 4 times smaller than the PFET.
Okay. Just because the gate length is now 4 times longer.
Yeah, exactly. I was trying just to make them as small as possible. Like if you did an actual layout for this thing, that divider could actually probably be shared between several level converter. Not too many because you don't want to carry that voltage too much, but you could probably do like a symmetric layout where you have like both the current reference M3 and M2, and then the voltage, the mid rail reference M11 and M4, like in the middle, and then on both sides have the differential pair. The first stage and the second stage, basically.
So you could share M4, 11, M2, M3, and M1 across, say, 2 channels.
Well, I mean, M1 you can't share it. You need a.
This is the yeah. But this could be the common.
Yeah, that node would be shared.
Yeah. Okay. So let's see if this
try and save a bit of space.
And if it's possible for me to load them now. All right, cool. So this is my crappy one, and it's finished a simulation across all of these. And then I don't really have a better way of doing this, but I can select which data set I'm showing. So you've got 2 waves there. And by changing this number, I can change the input and output signal. So it's kind of iteration 12. Well, I guess that would probably still work, but at 14 it goes wrong. So that's at a input of about 1.1 volts. It goes wrong. And above that, it's fine. So we've just seen with the experiment that things look like they continue working down to kind of 0.8-ish volts. So we really want a level shifter that can do better than this. So now we can simulate this one. And you don't have any graph set up, do you? But we can just plot this.
No. You could copy like your control block in that one, but
yeah,
I haven't made any fancier.
But there we go. We can see we've set that input to be 0.3 volts. And the output is still pretty nicely formed, full swing wave at 1.8 volts. So I'm definitely going to use your layout, your design. Do we have any questions from anyone about this or how this works? Otherwise, I'll start doing a layout of this and then aim to finish it off during the week. So I'm kind of tempted to just go with this as it is, Sylvain, rather than spend too much time tweaking the numbers.
Yeah, I think the only thing to do would be to at least try to split, because like if you want to match, it's better to at least have two fingers because it's easier to match. Although you're not too, I mean, in the end, you're not too concerned by offset voltage. Like if you have an offset voltage of 0.1 volt, it's gonna be fine. Like
Yeah.
it should still be toggled, so it's not critical. You could still, I mean, the differential pair, you could easily split it in two because 1.68 is 0.84 by 2. So yeah, all the weird dimension, by the way, 0.42 is the minimum width, and they're all multiple of that. So 0.42, 0.84, 1.68. I just usually stick to multiples of the minimum dimension.
Society of High Sciences is saying we're boosting DC pulses to match the required voltage. So, yeah, we're looking at a way of taking a tiny tape out design, which exists in this multiplexer circuit because it's one of hundreds of designs, and being able to control its supply voltage to see what happens as it is run on lower and lower voltage and the MOSFETs start operating in their kind of sub-threshold regions. Because there's somebody who's wanting to do a project based on that. So that means that the output of the design here could be very low, like 0.5 or 0.6 volts, and then it's not going to get distributed properly by the mux. So we have a level shifter here that shifts it up to the correct voltage for the mux. So that's what we're doing there. And Tatzel Brum is saying, are you even trying to use low voltage and matching techniques? I would say not really. We're just kind of hacking about.
Yeah, if I can answer, because Tatzel Brum said also output will limit your output voltage swing at low VDD. But that wall level converter circuit is powered by VDD, which is 1.8 volt and will stay 1.8 volt, right? That part of the circuit is not powered by the reduced VDD. So that's not an issue. The only thing powered by the VDD-L in that is the voltage divider providing SRCN.
And that's the comparator, which is kind of, that's providing the reference for the comparator, right?
Yes.
Yeah. So we kind of, we want that. We want it to scale.
Yes.
Yeah. Is the only reason you didn't want to use two resistors here because it's will be
Resistors
smaller?
are big.
Pardon?
Resistors are big usually.
Yeah. So just for the
compared to and mass.
Yeah. And so Tatzel Brum is saying, what's the problem with using the analog I/O pins for the low voltage experiments? The problem is that the analog I/Os go through their own mux. Welcome, by the way, Sam. So this was the idea of my idea here is that we would just put those very low voltages through the analog mux, but I'd forgotten that the analog mux uses transmission gates that are powered themselves by this voltage rail I'm planning to experiment with. And yes, Sam. So we took Sam. I was just you missed this, but we looked at your. This was the level shifter that you suggested a couple of weeks ago, and it works, but it only works down to about 1 volt. And Sylvain got curious and made a much cooler, more complicated. I mean, that one only uses like 4 or 5 transistors. This one uses like 8 or 9. But this one works down to. Do I still have that thing? No, down to like 0.3 volts. So this is the one that we're going to do.
Someone on Slack also had an interesting idea to use the native VT transistors. So the classic circuit that Sam suggested, it mostly stops working because you're just below the VT of the transistors, basically.
Mm-hmm.
But Sky 130 also has native devices which have no VT modification implants, and so they have like near zero threshold voltage. And apparently there's a way to use that to make like very sensitive level converter, but I didn't find any good paper or circuit that would make use of that. So if anybody has any reference on how to actually use native VT transistors to make level converter that can...
Is that this one? NVT?
Yeah, exactly. So those, they have near zero. They're near zero. Depending on which corner you have, they can actually be slightly positive or slightly negative. So you can actually have transistors which are always on. But yeah.
Sam says the more transistors you use, the better.
Yes, of course. That's how you judge. Like the more transistor, the better. That's how you judge a quality of a circuit. It's the number
That's
of
how you know.
transistors.
That's why digital's best.
Yes.
Yeah. Okay. So let's see if I can. Probably I'm going to go back and do this again, but let's just see if I can get it to work. So if I. I'll probably need to put this in its own little box, won't I, to be able to more easily export it. But I guess I could. This is kind of all I need, isn't it, for the net list to import into Magic. But I think I'm going to make a new schematic. Oops, it's doing something a bit funny. Okay. So that's got to be connected to source P, right?
Damn it, I just realized I was muted. You can't have in connected to source P because you can't have a port with one name connected to a net of another name. You need to rename source P to... Okay, if you try to generate the netlist, it's gonna complain.
It's going to fall over, is it? Oh yeah.
Yeah, net shorted. That doesn't work.
Well, I could guess I can just delete source P and put in directly there, can't I?
Exactly. That's like the one thing that annoys me the most. And the thing is, it's like in every EDA. It's in Xchem. It's in it's even in KiCad. Like it's in every EDA tool and stuff is that like one wire has one name and that's it. You can't have multiple names if they're connected together. It's just annoying.
All right. Okay, so I think we've got that now. So I come back up to my test bench. Oh, I need to also make a new schematic, new symbol. And then I should be able to add that here. And then let's adjust this so it starts at 0.6, goes down to 0.2 in 0.1 volt increments. Get rid of that, I think. And maybe change this back. The one problem, Sam, with your more transistors equals more better is it also means runs simulation slower. Not always better. Okay, and then here I should be able to do a LVS, set it as a sub-circuit, click the netlist button, and now I have level shifter 2.spice. And I should be able to import this now into Magic and get all these components made for me. Sam was saying that more current mirrors is more better. Yes, I think we can all agree. All right, so that is works now. But we should be able to load those waves now. Oops. There we go.
One thing that's annoying to do in simulation, I haven't found a good way of doing it in Spice and Xchem, is to have in the same graph, like the different corners.
Yeah, yeah. Even just having the corners easily kind of switchable, I find difficult. I think that might be something that Case is useful for.
Yeah, I think that's definitely. I haven't actually tried using it yet. Have you?
No, me neither. No, I keep meaning to. Okay, but we've got the level shifter now in the test bench that I made, and it's working down to a nice low level, even down to 0.2 volts. And I have the spice, so should be able to now close all of this. And then, I'm not using the right PDK. Now I should be able to import spice and get all my transistors and my input and output pads. So the next thing to do will be to arrange them into the laid out level shifter. Probably don't need all these guard rings. What do you think?
No, probably not. But some of the transistors might be better also, like split and then matched in the single transistor, basically. But
I don't totally understand what you mean there. You meaning
so
instead of having
usually,
two...
like usually if I have like two transistors that need to be matched, and then I have like them both with 2 fingers, I would actually create a single transistors with 4 fingers, and then wire the drain and source and stuff so that they're common centroid, basically.
Okay.
But then you can't. I mean, import SPI doesn't work that.
That's not going to work then, no. But
Yeah,
you can still get it to work with LVS because each transistor is extracted properly. Yeah.
Exactly.
Okay, sounds like a more advanced technique.
But as I said here, I'm not sure the matching will do. Like,
yeah, I think I'm just going to go for a quick and lazy layout. I'll probably record myself doing it and then play the speed it up so it only takes 5 minutes and share it next time. So yeah, that's just got to the top of the hour there. So I think that's good for today. Thanks very much, Sylvain, for joining. And yeah, next week, same time, same place, 5 o'clock on Mondays. And yeah, just a reminder to subscribe to the channel and give it a thumbs up, sign up to the mailing list, all that good stuff. Hope you all have a good week, and I'll see you next time. Whoops, just removed you instead of my screen. Yeah. Okay. Thanks, everyone. Bye-bye, Sylvain.
Bye.